All right, how's everyone doing? Kind of thinned out a little bit today. I guess so. What's that? Oh, I don't know. Yeah, I don't have time to go over this. I'll work it out and I'll post the answer online.
So you're for last team. The answer is there you go.
I'll put something out there so you at least know what it should have been. I think that problem was beyond the difficulty level of a problem that would be on a test. But that was, a good challenge problem to kind of give you an idea of some of the geometry that could come into play on those things.
Is it going to be like a right or wrong 0 or 100?
On what, that?
E for effort or?
Well, I'll look to see if your derivative was taken correctly. I'll see if, you plugged in the right information. Take a look at it. How your pictures look. How well organized things are. All right, well, last time we had stopped, I had begun discussing exponential functions, right? We talked about E and the natural base. I should put some water in this thing. So we're going to pick up with that today. And I put a bunch of things over here on the board. These are in the notes. Okay, the notes that I provide for you online, all these formulas that are up here are in your notes. So when I refer to them, you can look in your notes or up on the board. I just wanted to be able to point to them, and I knew the projector wasn't working. So last class, I tried to convince you that if you take the function f of x equals e to the x, I tried to convince you that the derivative of that was what? Itself, e to the x. I told you that's true, right? I didn't go into an explanation as to why, I just said it was. And I said that geometrically, it was very, very unique, meaning that it's the only function that behaves this way, where it is its own derivative. Now, if I was going to try and convince you properly, then what I would do is I'd go back to the definition of the derivative, which was a limit, and I would write f of x plus h minus f of x all over h. That's the definition of the derivative of a function, right? And so if I try this, you're going to see we're going to run into a problem. Watch. What is f of x plus h? So what happens if I take this function e to the x and I plug in x plus h? E to the x plus h minus f of x, which is e to the x all over h. And then you go and look at that and you go, okay, great, this is no good. If I try and plug in or replace h with 0, I get e to the x minus e to the x, which is 0. Over 0, I get some indeterminate form, right? Some 0 over 0 was bad, right? That's what we said. So I could do something here. On that first piece, I could, if I want, rewrite e to the x plus h as, not yet, hold up, as e to the x times e to the h minus e to the x over h. And that's just using the property of exponents, right? If you have the same base, right, if I say x squared times x cubed, everyone says that's x to the 5th, you add the exponents, right? X to the 5th, or x to the 2 plus 3. So I'm just going backwards from this. I'm turning that into this. Do you all agree with that? And then you have an e to the x here and an e to the x here, so I can factor an e to the x out. So I factor an e to the x out, and what's left up there is e to the h minus 1, and then all of this over h, right? That's what would happen. Now, h has no effect on this, does it? That's e to the x. So that doesn't, this is not being affected by h. So I could pull that out. And I could write this. The only thing that has to ever stay inside of a limit are things that the limit is affecting. So I can pull that out like this. E to the h minus 1 over h. Okay? Now, what happens if h goes to 0? E to the 0 is 1. Minus 1. I get 0 on top and on the bottom, 0. And I'm still stuck, right? And there's not going to be any algebra that we can do on this. You're just not going to be able to do anything. But at the end of, I don't know, I think we'll get to it today, probably next class. I'm going to introduce you to a very, very powerful rule called it's going to be called L'Hopital's rule. It looks like La Hospitals, but it's L'Hopital. Okay, L'Hopital's rule is going to give us a way of handling a limit that we can't normally do, that we get stuck on. Very, very powerful rule. But for right now, I just wanted to show you this. I'm trying to convince you the derivative of e to the x is itself. I'm stuck trying to show you. Once I get this rule, I'll come back to this and I'll show you what this turns into. What is it? What do you think it's going to be? What does it need to be?
1.
It needs to be a 1. This needs to turn into 1. Because if it turns into 1, then that's just e to the x and I'm done, right? But I still need to convince you that that's 1. All right? Not happening here, not happening today. So if we're willing to take just on faith right now that the derivative of e to the x is itself, then we can move forward. Is that all right if you take that on faith? As long as I promise I'll come back and prove that later? All right. With that in mind, we also have to deal with what if you have a function, but instead of e to the x, it's a to the x, where a is a positive number and a is not equal to 1. So if you recall from college algebra, this is just what we call an exponential function. E to the x is a specific exponential function. It is the exponential function where the base is e, right? But this is more general, isn't it? This gives you not only e to the x, but then all of them, right? 2 to the x, 5 to the x, pi to the x. Doesn't matter. As long as the base is positive and not 1. Why not 1?
Because they can't equal 1.
Why not? What if a is 1? It's 1 to, what's it 1 to any power? It's just 1, right? And that's a pretty boring function, isn't it? F of x equals 1. So when we define exponential functions, we make sure we throw out the possibility of the base being 1, because then it doesn't act like an exponential function. It doesn't have that curvature to it. It's just a flat line. So, okay. So what is the derivative then? The derivative, and again, you'll have to take it on faith, all right, for now, is itself, right? But times the natural log of a. Now, does anyone remember what the natural log function was from college algebra? I mean, there was exponential functions and there was log functions. Do you remember the relationship between the two?
Wasn't it 10? The natural log?
The natural log was base e. Log log was base 10.
Oh, okay.
They're inverse.
They're inverse functions. So if you have an exponential function, a to the x, the inverse of this function is log base a of x. So the relationship between exponential and logarithmic functions is that they are inverses each other. And that's what the first two sections of chapter 3 get into, going back and reminding you from college algebra about the relationship between exponential and log functions, which I'm not going to commit time to. So I recommend if you need to go back and review that, just read through this, go back to your college algebra book, take a look at exponential and log functions. All right? Any time I use a property that you have from college algebra, I will let you know. But if you're like, man, yeah, I wouldn't have known that, just remember I'm asking you to call on information from at least 2 semesters ago, right? College algebra? All right. All right, so anytime you take the derivative of a to the x, you're going to have itself, which we should expect that. But then you'll always have this. And this right here is always going to be a number, right? Because the a is a base. The a is a number. And so the natural log of a number is a number. All right? So let's see now why, when we do e to the x, if we were to use that formula for e to the x, that formula, it should be what? E to the x times natural log of e. But natural log of e is 1, and that's from college algebra. Why is it 1? Because they're inverse functions. That actually comes from this property right here. The natural log of e to the first power is 1. So natural log of e is 1. So this right here turns into a 1, which means the answer is e to the x. But it's the only one that would behave that way. Because the only way you'll ever get a 1 here is if that right here, if that is an e. If that's any other number, it's not going to be 1. Sorry? Like if you replace a with 10, then you're going to get 10 to the x natural log 10, but natural log of 10 is not 1. All right, so let's now look at an example. I want us to find the derivative of something. I'm going to let f of x be equal to x to the 4th plus 4 to the x. I want us to find f prime of x. So the only thing that this example is for is to illustrate something that you need to be careful with when it comes to taking derivatives. We're so used to the power rule now, where you pull the power out, right, and you subtract 1. We're so used to that students will start to do that when they can't do that, when they're not allowed to. So when we look at this, you have two terms, right, separated by addition. So you do derivative of each one separately. What's derivative of x to the 4th? 4x cubed. So that one, yes, that's power rule. You pull the 4 down, drop the power by 1, you're in business. Plus, this one, though, is not x to a power, right? It's a number to the power x. That's an exponential function. So the derivative of that should be what? Itself times natural log of 4. Totally different, right? Totally different. What is it that you think I see as the most common mistake for the derivative of this? What do you think I see that's a common mistake? x4 to the x minus 1. That's the most common mistake I see. You try and use power rule on an exponential function. Why do they call the power rule power rule? Because it's used for power functions. These are power functions. We call these power functions of x. X to various powers, right? That's different than this. A to the x, an exponential function where the base is a number, the variable's in the exponent. Exponential, power function. So the power rule is for power functions. The derivative of an exponential function is totally different. Are we clear? All right. Once we have this, though, we can combine this with with all of our other rules, so it can kind of start to be a little bit of a pain in the butt. So how about something like this? I'll give you as an example y equals e to the negative t squared cosine 3t. And we want to find the derivative of this.
Would you do a power rule? I mean, product rule? And then change it around?
Yeah, I think that you have product rule as the overall big rule here, don't you? Like you have a product, it occurs right here. There's your product. Yeah? So let me write down what the product rule would say. It would say I need to take the derivative of the first one times the second one plus the derivative of the second one times the first one. So that's just me writing out the product rule. I haven't taken any derivatives, right? Just writing out the rule. Now let's see how good we are yet. You know, see where we are. See where we're at. I can't even talk. See where we are at here. I have here for this derivative composition. I have e, but inside of e is not just e to the t or e to the x, it's what? Negative t squared. So negative t squared is sitting inside of the exponential function. So it's e of negative t squared. So that's chain rule, right? Anytime you have a composition, that's chain rule when you take the derivative. So I say, all right, what's the derivative of e to anything? Itself, right? And you don't have to worry about the little natural log e that comes out because it's always going to be a 1. So derivative of e to anything is itself times, now you have to go inside the thing that was plugged into the e function, which is what? Negative t squared, and you have to differentiate that, which would be what? Negative 2t. And that goes right here, negative 2t. Now I have a dot here to represent the fact that this is multiplication. That minus sign, you might mess it up and you might accidentally think you're subtracting here, so if you want to be real safe, just put it in parentheses. What's next? Times the cosine part. So I have done the chain rule on this. This is the appropriate derivative using chain rule on this piece. Then I have to follow it up with this cosine 3t. And then plus. And now I move on to the cosine. I have composition again. I have cosine. Inside that, I've got 3t. So I start with the outside. What's the derivative of cosine of something? Negative sine of that something. Times the derivative of what was in there, which is just 3. Am I done with chain rule on the cosine? Yeah? All right, so then that times e to the negative t squared. Let's clean it up. Were there any questions on the derivative, though? Just as far as getting the derivative? So y prime will be equal to, let's see, if I put all this together, the negative 2t, I'm going to pop that out to the front. Negative 2t e to the negative t squared cosine 3t. Now here I'll pop all constants I can out. Let's see, I've got a 3, I've got a negative, and then I've got the e. So why don't I do this? Negative 3 e to the negative t squared sine of 3t. You agree with that? That 3 does not multiply times that, though, right? That's 3t is trapped. Now, when I look at that, I'm going to realize I can factor out a GCF here. There's one GCF, but e to the negative t squared occurs in both, so I could pull that out. I mean, that would be okay as an answer, but I can go another step if I wanted to factor it. That's probably about as far as I'm going to be able to go. I don't see any identities in here that I can clean up or condense that down, so I'm good with that.
So this would be the full credit answer.
Yeah, I would take that too. This one would need a little work. Yeah. All right, so you see this just adds another layer onto what we can do as far as derivatives are concerned. We just need to be careful in recognition of when to use that rule for derivatives of exponential functions. That's not very nice. Let's try it. Y is equal to e to the tangent t plus tangent of e to the t. So you have addition, so you can do each one separately. The first one is going to be a composition, isn't it? And what's the outer layer of that composition? Or what's the first function you're going to take the derivative of there? E, right? So derivative of e to something is itself. Times, now continue the chain rule, secant squared t. Good. Am I done here? Done there? Right, so that's it. Plus, here, it's composition again, but it's reversed this time, right? The tangent's the outer function, the e is the inner function. So secant squared, be real careful here, secant squared of e to the t. So you remember, you have to say, what's the derivative of tangent of something? It's secant squared of that something, right? Then times the derivative of what was there. So what's the derivative of what's in here? E to the t again. Is there a GCF?
Secant squared.
No.
They both have secant squareds, but one of them is secant squared t. The other one is secant squared e to the t. So you can't pull a common. That's it. That's a good problem illustrating the difference between the order in which they appear, right? If the e is inside something or if the e is on the outside. All right, how about this? Y is equal to natural log of e to the sine x plus e to the x. Oh, shoot, hold on. Yeah, e to the x squared. Let me dang it. I don't think we're ready for this one. Hold on. I can change, let me change one thing in here, okay? Let's make this times x squared. Now, this problem is to get us to think about what we haven't done yet, right? Like, when you're sitting here and you're looking at this, you're thinking composition, right? Because you have natural log of something here. Inside, you have a product, right?
But inside product is chain rule.
And inside this product, that one's a chain, and right? You got some. This is kind of messy. Yes?
Separating them.
How do you mean?
The law, right? It's not one separate.
Okay, so yes, I'm going to try and separate it. But before I do that, we have not talked about what the derivative of natural log of anything is, right?
Right.
Okay, so we should already be going, well, how are we supposed to do this? Well, we can't, okay? If we don't know derivative of natural log yet, then we can't do this. But I do want to point out things we can do to this without doing any calculus. We have natural log of x times y. In other words, two things being multiplied, right? And according to one of the formulas, if you have any log, doesn't matter what the base is, natural log or log base 10, doesn't matter, that if you have two things being multiplied, I can split this into two logs, couldn't I? So this would become natural log of e to the sine x, what? Plus natural log of x squared. Couldn't it? According to this property from college algebra. And then, what about the first term? Still no calculus here. What's natural log of e to the sine x? Sine x. The natural log of e to something, the natural log and e wipe each other out. Remember, college algebra, they're inverse functions, right? So they undo each other. So this just becomes sine x, just from the properties of logs and exponentials together. And I can't do a whole lot on this one, but I can do one thing. So anyone see what we can do again using properties? I can bring the 2 out in front. The 2 comes out in front of the natural log, and that is using this property right here. This is an extremely important property from college algebra. It says that if you have a log, something to a power, the power comes out. Show of hands. How many of you remember that property, seeing that in college algebra? Okay. So just remember, if you have a power here, it can drop out in front. Or if you have a number out here, you can push it up as a power, right? It goes both ways, that property. So this derivative looks a lot better now, doesn't it? The derivative of sine of x is cosine x, plus, separately, 2 is a constant. It will come for the ride. I just need to figure out what the derivative of the natural log of x is, which I haven't told you yet, right? So I don't know. We'll revisit this in just a second. What is the derivative of natural log of x? Let's see. So what is the derivative of y equals natural log x? That's what we want to know. I know what the derivative of e to the x is, don't I? Well, I told you what it was, and I told you I can't prove it yet, right? But we all agreed that it was derivative of e to the x was itself. Derivative of natural log, though, I can actually show you this one. As long as, again, you still believe me that the derivative of e to the x is itself. All right? So I'm going to write down what I'm trying to find. Here's y is natural log of x. I want y prime. Everyone agree? All right. So what I'm going to do this is I'm going to be clever. I'm going to take e on both sides of the equation. I'm going to use a property of exponential functions. And that property I don't have written on the board, but it's this property here. It says e to the x equals e to the y, IFF, x equals y. Have y'all ever seen this IFF? If and only if. So what it means is this. An if and only if statement is the same as what's called a double implication, which means that if this is true, okay, if this is true, then that means it forces this to be true. So if e to a power equals e to another power, that means those two powers have to be the same. But it works the other direction. Meaning that if you have two numbers that are the same, then that means e to those powers must be the same. So if the arrows work in both directions, it's called a forward and a reverse implication, then that means you have if and only if. Very strong condition to have that in mathematics, an if and only if. I'll give you an example of something that's not an if and only if. I think I've shown you this before. X equals 2, if and only if x squared equals 4. Is this true? If x is 2, is x squared 4? Yes. If x squared is 4, does that mean x is 2? No, because x could have been negative 2, right? So this implication works this way, but not this way. So this could not be an if and only if. This could only be this way. Understand? But with exponential functions, this property is implication is both ways. So what I'm getting at is that if this equals this, right? That's like saying this line, x equals y. If these two are the same, then these two are the same, according to this. Understand? Using that property, what is the right side? X. Okay, the right side's x. So I have e to the y equals x. And then
Drag it over, right?
take the derivative.
Yeah.
Take the derivative now. But we're going to be taking the derivative implicitly with respect to x. Because remember, y prime meant dy dx. So be careful. What is the derivative of the left side with respect to x? So what's derivative of e to anything? E to it's itself, right? Times, but chain rule says now the derivative of what's up there. And what's the derivative of y? Dy dx, y prime. Now the right side is the derivative of x. And what's the derivative of x with respect to x? It's 1. And what were we trying to solve for? Y prime. Can you come back over here and solve this for y prime? Sure. Just divide by e to the y, right? So the derivative is 1 over e to the y. But what's e to the y? Come back right here. E to the y is this, right? But what did we say this side was? E to the natural log of x is actually, well, it's right here. E to the y is x, isn't it? So this is really what? 1 over x. E to the y is x, right? So if my answer is 1 over e to the y, then it's 1 over x. So the derivative of natural log of x is 1 over x. Yes?
Can you explain how you got e to the y equals x again?
E to the natural log of x is x using the property up there from college algebra. That these two kill each other off. Sorry, it's the one circled below it. E to the natural log of x equals x. It has to do with inverse functions. I don't know if you recall this, but in college algebra, if you were given a function and its inverse, right, then this was the property. If you took f and you composed it with its inverse, it spit out x. And it worked both ways. If you take the inverse and compose it with the function, then you get x. In fact, in college algebra, to prove that a function that you have found the function's inverse, you had to show this composition worked both ways. You remember doing that? It was a long time ago, but we did do, I know that in my classes we did do this. E to the x and natural log of x are inverse functions. This is f inverse. So if I put the e inside here, the x pops out. If I put the natural log right there for x, the x pops out. And those are those two properties right there on the board. So that's what happened here. I hope that clarifies that. That's what happened here. Yes?
So in our question that we were going to come back to,
Yes.
would it just be 2 over x since we're multiplying 2 to the inverse of ln x?
Yeah, let's go back to that question we had left. The derivative of that one would be cosine x, right?
Plus 2
Plus 2 times 1 over x. The 2 comes along for the ride. The derivative of natural log of x would have been 1 over x. And of course, yes, you could write that as 2 over x. Is that all right? This is finishing up the problem I had stopped at. Questions? Comments, concerns, gripes? All right, let's try something else. What if we have y equals natural log of, let's do it this way, negative natural log of cosine x. This is composition, right? You have a negative in front. That's just going to come along. But this is composition. It's natural log of cosine, right? Natural log of cosine. So I'm going to start out by writing out the negative, because it's coming with me, and then times, what is the derivative of natural log of something? 1 over the something, right? Because the derivative of natural log of x is 1 over x. But now, with composition, it's going to be 1 over whatever's in there. So 1 over, I don't like that. Negative 1 is the front, okay, times 1 over, what did you say? Cosine x? Am I done? No. Now I go inside, take derivative of what's in there, which is negative sine x. What does that negative and negative do over there? It becomes positive, so I'm just getting sine x over cosine x, which is tangent x. Huh. It's weird. We know the derivative of tangent is secant squared, right? But if I were to ask you, hey, what do you take the derivative of to get tangent? It might have been a little difficult to say, oh yeah, that's negative natural log cosine x, right? I don't know if y'all just follow what I said. Look, if I wrote this down, secant squared x, said, hey, everyone, that's the derivative of something, right? What is that the derivative of? Tangent x, right? Now, if I write down tangent x and I say, hey, everyone, that's the derivative of something. Negative ln cosine. That's not so obvious, right? That's what Cal 2 is. Trying to go backwards. If you integrated tan x, you get this. Yep. All right. Y equals natural log sine to the 8th of the square root of x. Find the derivative of this. This is kind of nasty. What do you have going on here? Composition, right? How many layers do you have to this?
3.
Okay, the outer layer is what? Natural log. What's the next layer in? Sine 8, which one is it? The exponent would be first. 8th power would be next. Then sine, then square root. Right? However, this does look like natural log of something to the 8th power, doesn't it? Which is kind of like the property here. You have any log, doesn't matter what log it is, and you have something to a power, what can you do to the power? Bring that out. Would you agree if I pop the 8 out, I don't have to deal with it in the composition?
Yes.
So let's try and simplify it if we can before we take a derivative. That'll save us one layer of chain rule, won't it? So you have to realize that that original problem really means this. This 8th power right here on the sine really means all the sine stuff to the 8th power. And that's what allows us to pull the 8 out in front. So this y is equal to 8 natural log sine of root x. So I have not taken a derivative there. That's a little cleaner, isn't it? Now derivative. So the derivative is equal to 8 comes along for the ride times 1 over sine of root x. You could put 8 over, yep. Now continuing chain rule times the derivative of what's in there, cosine of square root of x, times, are we done? 1 over 2 root x. That would be it. So this first part's the derivative of the natural log of this junk, times natural log's gone. Derivative of sine of the root is cosine of the root. Derivative of the root is 1 over 2 root. I can clean this. I'm getting 4 cotangent of root x over root x. What did I do?
Root x, root x.
Remember, this root x is trapped in the cosine. I was going to point that out too. Be careful not to try and do this, because then you're just left with cos, right? Cos what? You can't do that.
But you have to rationalize.
You could rationalize that. You don't have to, though. The important thing is this root's trapped, right? So you can't start messing with it. Yeah, the rationalization would be this, and then multiply those. That's x on the bottom, but you get a root x on top. So 4 root x cotangent root x all over x. But they're the exact same answer, and there's no need for us to do it. All right, we good? You're going to have to practice, right? I mean, this is obvious. You're going to have to practice, and this section has plenty of practice when it comes to taking derivatives. So remember when I started class, I said derivative of e to the x is itself. The derivative of a to the x is itself, but then you have to tack on that little natural log a thing, right? So what about the derivative of log base a of x instead of natural log of x? Yeah, what's going to happen here? So what if f of x is equal to log base a of x, then what is f prime of x? It's very similar to what we just had with the exponent one, a to the x. First of all, we know that it's going to be 1 over x. But we're also going to have a constant like we did before, right? Derivative of a to the x was itself natural log a, right? If this is e, then that's a 1, right? We're going to have a similar thing here. The derivative of this is that, but then on the bottom, times natural log a right there. That's the formula. So I'll give you a real quick example next to this. If y is equal to log x, what's y prime? What's the base of log if I don't write the base? It's base 10, isn't it? You need to remember that. So this is really log base 10 of x. So a for us in this problem is 10. So the derivative of that should be 1 over x, right? ln 10. So it's almost the same as the derivative of natural log of x, except you have to scale by this little thing. This is just a number. Does that seem weird? Or I'm asking you to just believe that this is true. Is that all right with you or not? You don't like it? Okay, you don't like it. I'm going to make it real quick here. Log base a x, you ready? I'm going to prove that it is real fast. You don't need to copy it down to see if you follow it. What I'm going to do first is take a to the y, both sides. Now the reason I do that is because what does this become? A to some power and log base a, those are inverse functions. They're going to cancel. It's, well, it's again, I'm using these properties, but with a for the base. So the right side becomes x. The left side is just a to the y. Now I take the derivative on both sides. The derivative on the left side is itself times natural log a. See, that's the difference. Times y prime. So what's the derivative of a to anything? itself times natural log a. Then what's the derivative of what's up here? Y prime. What's the derivative of the right side? 1. Then you divide through, y prime equals 1 over a to the y times natural log a. Do you agree? And then what's a to the y? Is x. So there it is. Okay? Same basic concept of how I got the derivative of natural log of x. All right, well, how are y'all feeling? It's okay. You're going to have to practice this. I was a bit disappointed. I did catch up on my grading. I was a bit disappointed with the chain rule. Of course, I don't have enough time to grade every problem, but I just looked and there was about half the class attempted 90%, 95% of the problems, and like another half of the class that attempted about half the problems. So I'm just concerned for that half that didn't really get through all the chain rule problems. That, you know, if you can't do chain rule, you can't do what we're going to do now, and you're not going to be able to do what we do later. And so you've got to get the chain rule down, right? So just make sure you're trying to keep up with it and go get help. You know, whether it's coming to me for help. I know that I've helped only a few students in this class. My Cal 2 students are always in my office, but you know, I can't force you to come get help. But I'm offering it. So please grab your stack of chain rule problems out of here. It was graded mostly on what I could tell effort-wise. I thumbed through it, make sure that most of the problems were there, made sure it didn't look like just copied out of a solution manual type thing. So if you want to dispute your grade with me, you can. All right. Now, in this section, the derivative of e to the x, natural log x, a to the x, log base a of x, that's the main result of these sections. And so I will, is this the take home? Okay, quiz. So I will summarize for us the results, the main results that we need moving ahead, all right? And put them over here to the side. You help me out. What's the derivative of e to the x? Itself, right? Okay, what's the derivative of a to the x? A to the x, ln a, right? What's the derivative of natural log x? 1 over x. What's the derivative? How do I write this? This is e to the x. This is a general one, right? This is natural log is log base e. What's a general log base? Log base ax. That's the general form of a log. What's the derivative of that? 1 over x, natural log a. All right. That's the main results of today and a little bit of last class. All right. All these formulas are on your formula sheets. You know how you have those formula sheets? If you look at those formula sheets, it's all there, except they use u instead of a. I mean, instead of x. They go e to the u, a to the u, natural log u, log base a of u. We can use product rule, chain rule, quotient rule. All the rules apply with those new functions.
So now we can pretty much do these.
Now you've pretty much have opened up all things you've seen, right? There's no other functions out there that you've messed with that we haven't taken derivatives of yet? Can you think of a function we don't know how to differentiate?
Well, inverse, cosine.
Arc sine, arc cosine. It's coming. It's coming. So there are some out there we haven't. All right, well, you would hope that's the end of this section, but the last part of this section, the tail end of it, is the more difficult part of this whole concept, all right? So we're going to look at what's now called logarithmic differentiation. We are in 3.3, hold on. Yeah, 3.3, still in 3.3. I'd like to open this with an example. Let's let y be equal to e to the negative x cosine squared x over x cubed plus 1 to the 7th times x to the 4th minus x minus 1 to the 9th power. Now that's one of the uglier functions you've ever seen in your life, right? I mean, that's a pretty nasty looking thing. It's got a lot of different stuff happening in here. E to the negative x, it's got an exponential function mixed in with a cosine function. It's being squared. On the bottom, you've got some polynomial functions. It's a disaster. If I asked you to take the derivative of that right now, could you do it? I mean, like, could you set it up and start going through the process?
Sure.
Yes. What would be the overwhelming thing happening here? Quotient rule. So you'd have to set up what? The derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared, right? And when you do the derivative of the top, you're going to have what? Product rule. And then within that product rule, you're going to have some quotient rule, right? Why did I say quotient rule? Chain rule is what I meant to say. Thank you. So within the product rule, you're going to have some chain rule. That's going to be a mess. Then when you get to the derivative of the bottom, you're going to again have product rule, and then each one of those has chain rule. That's like torture problem, isn't it? You could do it given long enough time and a wide enough page, right? But that would not be fun, right? So let's see if we can employ this thing called logarithmic differentiation. The great thing about logarithmic differentiation or logarithms are all these properties we have that allow us to split up, right? When we have products, we can split into two logs. When we have quotients, we can split into two logs, right? Yeah? When we look at this, though, we don't have a log. Like, we can't just start splitting things up unless we have a log, right? So what I'm going to do to start the problem is I'm going to take the natural log of both sides of the equation. Now, am I allowed to do this? Well, there is some property somewhere that says this. What do you think it says after this? Yes. So that's, again, from college algebra. Natural log of x equals natural log of y if and only if x equals y. So that means that if I'm saying x equals y, this equals this, then natural log of that equals natural log of this. Yeah? Now, what have we gained here? What can I do on the right side? If I have the natural log of a quotient. Notice I haven't done any calculus, right? I mean, I'm not doing any calculus yet. This is all algebra. So if I have natural log of a quotient, I can split it up into two logs with subtraction between the two. Right? Okay. So this becomes, keep the left side there, natural log y equals, I have two logs. Natural log e to the negative x cosine squared x minus natural log, shoot, I'm out of room. I'm going to have to come over here and do it. I need a wider page here. Natural log y equals natural log of e to the negative x cosine squared x minus natural log of x cubed plus 7, no, x cubed plus 1 to the 7th, and then times x to the 4th minus x minus 1 to the 9th. That's it.
Would you use the brackets instead of the parentheses? parentheses.
You could, it's up to you. Brackets and parentheses have the same weight in mathematics. There's no difference between the two.
Yeah, I didn't know.
What's that?
I didn't know what the difference was either. If there wasn't.
Yeah, you know, like when you're first learning like order of operations, and you go way back in the day, when they wanted you to do like 2 plus 3, and then like plus 5, but then that minus 2, and then they use a brace. Remember something like that? The only reason they did that is because they think at that point you can't handle all the parentheses. So they use different symbols to help you distinguish between where things are broken up. But this is totally the same as, oh, I'm sorry, I forgot to turn my phone off. Let me silence this. I keep forgetting to turn this off. There's no difference between that and this. That's the same thing. It's just that, again, when you go back and you're, I don't know how old you were when you did that, but when you look at that, you might be like, oh, you know, when you look at this, you're like, okay, these go together, and then the brackets go, you know? So it's just a thing we use to help. But, I mean, because what if you needed more? You're going to run out of symbols if you keep using that, right? What are you going to use after braces? You know, you make up your own shit, right? You're like, whatever that is, you know. You'll run out eventually. All right, what now? Are you ready to take the derivative? I mean, if you take derivative here, you're going to have to do derivative natural log of something, right? Which is 1 over it, but then you have to do derivative what's inside, which is a product rule. You want to start messing with that? No, wait, you would have to use what rule in there? Product rule, because it's a product, right? But wait a minute, what can I do with products, with logs? I can turn it into 2. So this right here can turn into 2 logs, and there's a product there. This right here could turn into 2 logs, couldn't it? So I'm going to write that out. So natural log of y equals, help me out, natural log of e to the negative x plus cosine squared x. Okay, now be real careful here. Minus
Natural log of
and then
And natural log.
what natural log? Plus natural log?
Well, it's-
This product turns into addition, doesn't it? But this minus is in front of all of that. So look, I'm going to put brackets. No, I'll put parentheses. This is what I'm about to split into 2 pieces, right? It's going to become natural log, then plus another one. Then that minus would have to distribute to each one. So it's going to be a minus here. I'll put it in red just so you're clear that that minus is something people get tripped up on. Natural log x to the 4th minus x minus 1 to the 9th. That's a little better, right? I'm still preferring this to doing all the rule stuff we would have had to have done. I'm still preferring this.
It's still no calculus.
Yeah, it's still not calculus, though. Okay, natural log of y. What's that? Negative x. Right? Natural log and e cancel out. You just get what's up there, negative x. No derivatives yet, right? What can I do here? Bring the 2 out front. Because the 2 is the power on the cosine, isn't it? Here? I can bring the 7 out front. Oh man, I'm just like wiping out a bunch of work, aren't I? And then here, what can I do?
Minus 9.
Bring the 9 out front. Man, we have just saved ourselves a tremendous amount of effort by doing that. Is there any other things I can do with the rules?
You can't add them all up.
Can you do what?
Can you add them all up into one of the natural logs?
Mm-mm.